Peptide bonds are how we link amino acids together. These are the same things as amides. And so actually, when we've made amides before in this class, you already learned how to make a peptide bond. And that's the cool thing about it. So we need to make sure that we're writing the nitrogen side on the left, and that's defined as the N terminus. On the other hand, the COO is the C terminus, and that's going to be on the right. So if you're going to combine amino acids to form an amide bond between two amino acids, what ends up happening is where this COO is right here reacts with where this NH3 is. Just like we did before, we have an oxygen and two of these hydrogen that go into making water, okay? Sorry, I covered that up a little bit much. That's what goes into making water. Now, it may be the case that, you're only using two of these hydrogen that are right there. Why is that? Well, the nitrogen that's right here, notice he's got a hydrogen still left on him. And so you need to keep one there. Then this COO bond is still there from one side to another. Okay, so we keep that intact. And this is the new bond right here in between those two guys. And that's how we link amino acids together. Now, this would be phenylalanine and glycine. And when we're naming these guys, we just kind of combine these things. But we take off the INE at the end of phenylalanine and we replace it with YL. So this kind of sounds funny, but it's phenylalanenyl glycine. So you do that for the first word or anything that's before the last word. You take off the INE and put YL. Or we can use abbreviations. We can use the 3-letter abbreviations because I don't know about you all, but a lot of that writing out of huge amino acid, that would be huge, right? That would be a lot of stuff to write. So we could go with 3-letter abbreviations or we can go with 1-letter abbreviations. It's usually expected that if you can see maybe a diagram or one of those charts that has these things listed on there, including their 3- and 1-letter abbreviations and their names, that you can go ahead and write that up. And so you would be able to predict what the peptide name would be. So if you are going to combine methionine, tyrosine, and asparagine, you could put it as MET-TYR-ASN. So that would be one way to write that. Or we can write it methionyl tyrosyl asparagine. That's all one word. That's kind of crazy. Or just simply MYN. So sometimes those things don't end in INE like I mentioned. Sometimes they end with AN or ATE. All of those terms just get replaced with that YL. So when we're talking about larger structures, then we need to sort of define what happens when we get to a protein structure. Well, there's ways that proteins fold, and they're so complex that we have to talk about them literally in 4 ways. We call it primary, secondary, tertiary, and quaternary structure of a protein. Okay, this really isn't difficult. It's just a matter of figuring out what you're talking about. Let's say you have an amino acids of over 50, a protein sequence over 50 amino acids, because that's sort of what we define as a protein. Each type has unique means of folding and all that good stuff. So what we start with is known as the primary structure, and this basically means what's the order of amino acids that are linked to one another. So serine is connected to valine, connected to phenylalanine, connected to tryptophan. Okay, so that's easy. Which way do they connect to each other? Next, we get to what's known as a secondary structure. On secondary structure, this is like little regions of this huge amino acid, usually it's way over 50 by the way, and how they begin to fold. So I want you to consider sort of like a big string. If you were to start twisting it, what ends up happening is you get these little twisty-doos that happen in the middle of it. Well, that would be one type of secondary structure. And in proteins, we call that an alpha helix. And alpha helices start where NH and CO portions of amino acid can hydrogen bond. That's what makes that happen. So hydrogen bonding makes this thing happen. And in smaller amino acids, usually, but not always, we have what's known as beta sheets. And here, like a whole bunch of things just sort of stack up to each other and like it folds back on itself in order to create these little pleated type of things, sort of like a fan would look. And this is also held together by hydrogen bonding between, guess what? Exact same things, the NH and the C double O bond, which means that the secondary structure is really held together in large part by hydrogen bonding. So you may have several areas within a protein that contain regions of alpha helices or beta sheets. Just to let you know, a good beta sheet that you know of already, it's called silk. Or collagen you may have heard of, which is something that keeps your skin nice and bouncy. And that's kind of like a triple braided alpha helix or a triple helix. Okay, so secondary structure is regions of things that start to fold in a particular way. Next, we get into the tertiary structure. As you might imagine, this is not going to be regions, but it's the entire protein, how that folds together. There are several different things that we have to keep in mind here as to what makes a protein fold. And it's not all going to fold the same way. There's areas that fold this way or that way, and then the rest of it just does crazy stuff. But the interactions that make all of these things possible to come together. We have hydrophobic interactions. This is where nonpolar R groups kind of just cling together. Hydrophilic interactions. Polar R groups kind of cling together. The things that are nonpolar tend to go to the center of a tertiary structure because they stay away from the fact that the rest of your body is made out of water. And so those are going to go towards the outside of that structure, okay? Next, as we've already talked about with other stuff, we have hydrogen bonding that's there. So hydrogen bonding can happen between amino acids that's not necessarily an alpha helix or a beta pleat. It just happens. Next, we have what's known as a salt bridge or salt bridges. Now, this is when two R groups can come into contact that are ions. And so you have an actual ionic bond that hold things together. Now, the final thing would be a disulfide bond. So this is when two SH groups come together. And remember how we talked about disulfide bonds earlier? And they make an actual bond. So that's an actual bond. This thing is really strong, okay? So tertiary structures can form things like globular proteins. That just means, hey, it's a big old glob of stuff. Or if you have things that are like long and stringy, we call those fibrous proteins because they look like fibers. We're really creative in how we think of things, huh? Finally, we have what's known as the quaternary structure. Now you might think there's nothing left. How do we have something that's quaternary at this point? Well, quaternary structure comes from the fact that a protein often, like all the amino acids that are linked together in one big glob, doesn't work by itself. Just like if you are trying to lift up a really heavy couch, you're going to need somebody else to help you. Proteins are built that way too. So quaternary structure has to do with how one protein interacts with another protein, because oftentimes two or more things have to come together to make a job happen. Okay, so that's what we're talking about with quaternary structure. Now, just like with building proteins, we can take them apart. And that's what we refer to as denaturing proteins. There's several different ways to denature or rip a protein structure apart. And these involve breaking the hydrogen bonds, breaking the salt bridges, breaking all of the things that we just told you, or I just mentioned here, about what's required to put together proteins. So things that do that. Agitation, what that means is mixing it really intensely. Heat, change in pH, addition of either organic solvents or compounds, and finally, heavy metals and ions. Now, the first set of these things you may recognize as things that you do when you're cooking, because that's indeed what you're doing. When you're heating something up, you're disrupting the proteins. Like when you heat up an egg, you're disrupting its proteins. There are ways to cook with change in pH and adding vinegar or something like that. Now, I would not eat anything after you add an organic solvent. Please don't do that. Or a heavy metal or ion. Don't do that either. But those are other ways to disrupt the structures that we're talking about that we just built. And that's it on proteins. I'll see you next chapter for enzymes.